So, in unstable nuclei decay, there are generally five types of decay processes that they will undergo. The first is alpha emission, then there's beta emission, positron emission, electron capture, or formerly known as K capture, and gamma emission. The way that you can tell which of the five types is occurring is by comparing the mass number and the atomic number of both the original parent isotope and the daughter isotope. That would be the isotope that remains after the decay has occurred. The first two types that we'll take a look at and then have some guided practice and independent practice with are alpha emission and beta emission. And then we'll touch upon the other three types as well. So in alpha emission, a lot of times these different decay types are indicated by the Greek letter for the type of emission. So you see the symbol for alpha there. And so whenever you see this, this is an indication of the emission of an alpha particle, which turns out to be the nucleus of a helium atom, 2 protons, 2 neutrons from an unstable nucleus. Because the alpha particle is made up of those 2 protons and 2 neutrons, that means that the daughter isotope is going to have an atomic number that's 2 less than the parent and a mass number that's 4 less than that original parent isotope nucleus. So here we see the alpha decay of actinium-227. You can see the first particle listed there is the helium nucleus. You don't always see the positive 2 charge written with it. It's mainly just He, 4 for the atomic mass and 2 for the atomic number. But it is a charged particle. And so then the daughter isotope is what remains when we subtract those numbers out. We get 223 for the mass number, 87 for the atomic number, which makes it an element, an atom of the element francium. So the daughter isotope would be francium 223. Beta emission, usually indicated with either beta or beta minus, you have a beta particle, which is essentially a high-speed electron that originates from the unstable nucleus. And so because we get an electron coming out, an electron we don't typically think of as emerging from the nucleus. We usually think of them as external to the nucleus. But what happens is you have a neutron in the nucleus that converts into a proton and an electron. The proton stays behind, so the atomic number of that isotope is actually going to increase by 1. But the mass number will stay the same because pretty much a proton and a neutron are just about equal in mass. The electron then gets ejected from the nucleus, and hence you have the beta particle. So if we take actinium-227 once again as our parent isotope, this time undergoing beta decay, you can see the symbol for a beta particle, E for the electron. Electrons essentially have 0 mass, so that's why the mass number is 0. And the atomic number is written as -1 because when you compare a nuclear equation, instead of, unlike a chemical equation where you have to make sure that the count of the elements on both sides balance out, in a nuclear reaction, because you are quite literally changing the identity of the isotope, you have to make sure that the mass numbers balance and the atomic numbers balance. And so if the atomic number is going to increase by 1 to give us, in this case, thorium-227, we have to make sure that the math will work out. So 90 plus a -1 gives you 89, which matches up with what we see for the parent isotope. All right, so looking at some practice, write the equation for the alpha decay of neptunium-226, circle the decay particle, and underline the daughter isotope. So here we can see we start with the parent isotope, and then we indicate the decay type over top of the arrow, and then we see our product particles that we get there. And so the decay particle is the helium nucleus, and the protactinium-222 would be the daughter isotope. All right, next example, write the equation for the alpha decay of thorium-221, again circling the decay particle and underlining the daughter isotope. And so here we see the parent isotope, the decay type indicated, as well as the decay particle. If we do the math, all right, we should take 4 away from the mass number, which would give us 217, and 2 away from the atomic number, which would give us 88. And consulting a periodic table, we see that element 88 is radium. So radium-217 would be our daughter isotope. Again, helium particle is your decay particle, radium-217 is the daughter isotope. All right, I'll try this one on your own. Write the equation for the alpha decay of radium-240, circle the decay particle, and underline the daughter isotope. You can go ahead and pause the video if you like to try this on your own, and then restart to check your answer. So in writing your equation, you start with the parent isotope, indicate the decay type above the arrow. You can either write it out or you can use the Greek letter that corresponds to it. But you should get helium 4/2 for the decay particle and radon-236 for the daughter isotope. We try some beta decay practice now. Write the equation for the beta decay of radium-230, circling the decay particle and underlining the daughter isotope. So in the first one, we see the radium-230 parent isotope, indication that it's beta decay. And then we see our beta particle, the E with the 0/-1. And as a result, that's going to give us an isotope of actinium-230. Again, the atomic number goes up by 1. And again, that's going to change the identity of the isotope. So our beta particle is the decay particle. Actinium-230 is the daughter isotope. Write the equation for the beta decay of neptunium-227, circling the decay particle and underlining the daughter isotope. So we see the parent isotope, neptunium-227, the reaction arrow with the decay type written above it, and then we see our beta particle. And if we do the math, we know the mass number is going to stay the same at 227. The atomic number is going to go up 1 to 94. This is an atom of plutonium. So our daughter isotope would be plutonium-227. Write the equation for the beta decay of actinium-214, circling the decay particle and underlining the daughter isotope. Why don't you go ahead and pause the video, try this one on your own, and then restart to check your answer. So in starting off our equation, actinium-214 with the reaction arrow and beta indicated above it, right, you should get your beta particle, E0/-1, for the decay particle, and in this case we would have thorium-214 as our daughter isotope. So beyond these guided practice problems in your notes, you have some independent practice that you can continue working on and give yourself some extra practice with both the alpha and the beta decay types. Now, those other three types, again, we're just going to touch upon, and then we'll do a little review here in the video. But positron emission, the symbol for that is beta plus, and that's because a positron is essentially a positively charged electron, if you will. It's the antiparticle to an electron. Like beta particles, they emit from an unstable nucleus. And, a positron, you can kind of see it in the name, positively charged electron. Basically, it's the reverse of beta. Remember, in beta, we have a neutron that converts into a proton and an electron. So positron emission is going to result in the opposite process. A proton is converted back to a neutron. And so because of this, the product of positron emission, has an atomic number that is going to be one less than the original nucleus, and the mass number is still going to be the same. So if we take actinium-227, notice this time it's beta positive. So you want to pay attention if there's a sign with the beta symbol. Your decay particle looks very similar to a beta particle, except there's no negative sign with the 1. And again, that's so that the math works out when we're balancing mass numbers and atomic numbers. So you have the positron plus radium-227, atomic number 88. Electron capture is another method of radioactive decay. This occurs by the nucleus capturing one of the inner core level electrons. And this used to be referred to as K capture because before we got into naming 1s, 2s, and levels that way, they had different names based on letters, like the K level electron. So this is also known as K capture. Proton gets changed into a neutron, very similar to what we saw with positron emission, except your particle is not a positron being emitted, rather, it's an electron um, serving as a reactant, if you will. So when we look at the equation, you'll notice the difference in where the decay particle actually is located. Um, in electron capture, what happens for your daughter isotope is that the atomic number is one less than the original nucleus, and the mass number is going to stay the same. So it's very similar to beta decay, but again, the difference is going to be that the electron, you'll notice, is now on the left-hand side of the reaction. Another interesting thing about electron capture is that in addition to that change that's happening with the nucleus, you also get emission of X rays. And this happens when an electron from further out comes down and fills in that gap that's been created when the electron's captured by the unstable nucleus. And so, as it's coming down to a lower energy level, that energy has to be emitted. And that's what the H times nu, or HV, Planck's constant times the frequency, represents. Finally, we have gamma emission, represented by the letter gamma. This is usually an accompanying type of radiation um, from the unstable nucleus. And because it's pure energy, there is no change to the atomic number or the mass number. So if all you're representing is gamma emission, there might be like a little asterisk or some kind of footnote symbol to indicate that it's gone to a more stable position. But other than that, there is no change to the identity of the isotope itself. So if we look at these examples, all right, we can key off of what the changes to the mass number and atomic number are to help us determine what the missing particle is going to be. We can look at the decay particle itself, and that should help us to predict the daughter isotope, but also the decay type. So the first one we see here is plutonium-242, and that's going to, we see helium 4/2, that's our decay particle, and we know that to be an alpha particle. So it's going to be alpha decay. And if we do the math, we see that the mass number comes down by 4, so 238. Atomic number decreases by 2, which is 92, and that corresponds to the element uranium. So again, this is alpha decay. In the next one, we have aluminum-30. We notice a beta particle there on the product side, an electron on the product side, so it's beta decay. And so the mass number is not going to change. It'll be 30. And in beta decay, the atomic number goes up by 1. So that goes to 14, which is silicon. So you have silicon-30. Again, this would be beta decay. Iron-55, now we see the electron is on the reactant side. So that's electron capture or K capture. And so the mass number stays the same at 55, but our atomic number is going to come down by 1 to 25, which is manganese. And so we have manganese-55. That's the product of our electron capture. Finally, the parent isotope is missing here. So what we have are the decay particle and the daughter isotope. And we see E with 0 over +1. So that means this is positron emission. So the mass number of the parent isotope is going to be the same, 93. And the atomic number is actually 1 higher than the daughter isotope. So it's going to be 44. And so what we get is ruthenium 93 for the parent isotope. And again, this is